first of all, if we want to verify Green's theorem, or if we want to apply Green's theorem, we need the curve to be a closed curve. Now, as per the question, C is the curve bounded by y equal to x and y equal to x square. Let's draw those two curves. We draw x-axis and then y-axis. We don't need negative value of x and y, so we need not take. Y equal to x, that's a straight line, inclined at an angle of 45 degree with respect to x-axis and of course in anti-clockwise direction. Say this is a 1, 0. Then when you take x equal to 1, y is also 1. So this is the point 1, 1. Let's draw the line y equal to x. Well, we have the line y equal to x. What about y equal to x square? That's a parabola. We can see that y is always positive. So we draw the parabola y equal to x square. We just need the rough parabola, so we have y equal to x square, but what is important is direction. So what do you think should be our closed curve? Well, we can have many. Let's take this point to be O. Let the point of intersection of y equal to x and y is equal to x square be A. And let this point, we take a point P on the parabola. And let us take a point Q on the straight line. Let us take a point Q on the straight line. Then we have a closed curve OPAQA. We should make sure that that is in anti-clockwise direction. OPAQO. So we have a closed curve OPAQO. We have a closed curve OPAQO. Okay, we have a closed curve OPAQO. Now we need to verify Green's theorem. Green's theorem states, let's write the statement of the Green's theorem, or rather exact formula that we need to verify. By Green's theorem, integral over closed curve f1 dx plus f2 dy equal to integral over region del f2 del x minus del f1 del y dx dy. Well, we may have dx dy or dy dx. That depends on the circumstances. Given we are given integral over closed curve xy plus y square dx plus x square dy. So Green's theorem says integral of a function f1 with respect to x and integral of another function f2 with respect to y over that closed curve. If we add it, then we'll get integral over region del f2 del x minus del f1 del y dx dy. We are given xy plus y square plus x square dy. So obviously we should take f1 equal to xy plus y square and f2 equal to x square. Now let's compute RHS. We believe that will be much easier for us. RHS equal to integral over E, whatever be that region E, del f2 del x minus del f1 del y dx dy. Okay, so we need del f2 del x minus del f1 del y. Now del f2 del x minus del f2 del x minus del f1 del y equal to your f2 is x square, so del x of x square minus del y of xy plus y square. If you differentiate x square with respect to x, you get 2x. If you differentiate xy plus y square with respect to y, you get x plus 2y. 2x minus x is x, and you have minus 2y here. Okay, is that enough? No, we need to integrate this function x minus 2y del f2 del x minus del f1 del y, that is x minus 2y, with respect to x and then with respect to y, or with respect to y and then with respect to x. So your right hand side is integral over region. Let's look at the region here. We need to just cover up the area bounded by parabola and the straight line. Now we just need to cover this area. we see that if we change y from y equal to x square to y equal to x, then we will exactly cover the area, but we'll have something more. We'll have something more here as well and something more there as well. So we need to change x from 0 to 1, and then first we need to change y from x square to y equal to x, and then we should change x from 0 to 1. So we can write RHS H first of all, we have del f to del x minus del f1 del y dx dy, that is x minus 2y. Therefore, RHS equal to integral over e del f to del x minus del f1 del y, that is just x minus 2y dx dy. Now if we look at this curve, if we look at the region, then we just need to change y from y equal to x square to y equal to x, and then x from 0 to 1. Therefore, RHS equal to y has to change from y equal to x square, y has to change from y equal to x square to y equal to x. At last, x has to change from 0 to 1. That will give us the region E, and then we need to integrate the function x minus 2y. X minus 2y, but we will integrate with respect to y first, and then at last with respect to x. We should remember that inner integral is to be evaluated first, and then once again we will integrate with respect to y first, and then at last with respect to x. And in case of double integral, we regard x and y to be independent of each other. So we have the function x minus 2y as it is. If we are integrating with respect to y, then we'll treat x as a constant. So this is equal to integral of x with respect to y is x into y. Integral of 2y with respect to y is y square. And our y is changing from y equal to x square to y equal to x. At last we'll integrate with respect to x, and x will change from x equal to 0 to x equal to 1. x is changing from 0 to 1, we'll integrate it. But more than that, let's put upper limit and lower limit of y. X as it is, x as it is. If we write y, if we put upper limit, you have y equal to x minus y equal to x square. That's your upper limit. Then if we put lower limit, x it is y equal to x square. Instead of y, we need to write x square, but we have y square there. Once again, let's check it. X as it is. In place of y, we can write x. In place of y, we can write x. So upper limit done. Lower limit, x as it is. In place of y, we can write x square. In place of y, we can write x square. Well, x into x is x square. We can cancel it out. And so we have this equal to x is changing from 0 to 1 minus x cube plus x to the power 4 dx. Well, that's the simple integral. Integral of x cube is x to the power 4 by 4. X to the power 4 is x to the power 5 by 5. And your x is changing from 0 to 1. If we write upper limit, you'll have minus 1 by 4 plus 1 by 5, and that is equal to minus 1 by 20. That is our RHS. Let's compute LHS equal to integral over closed curve f1 dx plus f2 dy, and that is your integral over closed curve. Here f1 and f2 are given in the equation. Integral over closed curve xy plus y square dx plus x square dy. Now if you look at the figure, the closed curve consists of moving from O, or you can start from any point, but I always move in anticlockwise direction. From O we may move along the P to the point Q, A, and then from A through Q back to O. So we have two kind of curves. One OPA, that's a parabola, and another one AQO, that's a straight line. So we can write this integral is, we can write it as integral along OPA, integral along OPA, the given function xy plus y square dx plus x square dy plus integral along AQO plus integral along AQO xy plus y square dx plus x square dy. Let's deal with those cases one by one along OPA and along AQO. Let's consider the first case. case 1, case 1 along OPA. Along OPA, you always find that y equal to x squared. So let's write y equal to x squared. So can we evaluate this line integral? Yes. Y equal to x squared. So dy by dx equal to 2x. So dy equal to 2x dx. Also, whenever we have line integral, we need starting point and ending point. We are moving from O to A at O x equal to 0, at A x equal to 1. So x is changing from 0 to 1. So, therefore, integral line integral along OPA xy plus y square dx plus x square dy. In place of y, let's write x square. And we are changing, we have x is changing from 0 to 1. So x is changing from 0 to 1. X as it is, dx as it is. In place of y, just write x square. In place of y, just write x square. In place of dy, just write 2x dx. So x is changing from 0 to 1, x into y. So y is replaced by x square. Y is replaced by x square. X square as it is, dy is replaced by 2x dx. We have dx here as well as here, so let's write x is changing from 0 to 1 here as well. Now can we evaluate the integral? Of course, yes. This is equal to 0 to 1 x cube plus x to the power 4 plus 2 2x cube. X cube plus x cube will give you 2x cube plus x cube will give you 3x cube. So 3x to the power 4 by 4. Integral of x to the power 4 will give you x to the power 5 by 5. X is changing from 0 to 1. So that is 3 by 4 plus 1 by 5. That's equal to 19 by 20. That's case 1 along OPA. But that doesn't end here. So that doesn't end the LHS computation. We also have along AQO. We need to do line integral along AQO as well. Along AQO, y equal to x. case 2 along AQO y equal to x. What about case 2 along AQO y equal to x? And what about change in x? You see, as you move from A to O, x is changing from 1 to 0. Comma, x changes from along AQO, x changes from 1 to 0. Along AQO, x changes from 1 to 0. Okay. AQO, x is changing from 1 to 0. Therefore, integral along AQO xy plus y square dx plus x square dy equal to, we observe x is changing from 1 to 0. X is changing from 1 to 0. We replace y by x, dy by dx. Rest x as it is. We are replacing y by x, dy by dx. So, x squared plus x squared plus x squared, that's 3x squared. If you integrate it, you'll get 3 into x cubed by 3. That is 0 minus 1, that is minus 1. Now we just need to add what do we have along case 1. We just need to add what we have in case 1, 19 by 20, and in case 2 case 2 we have integral equal to minus 1. Therefore LHS equal to 19 by 20 minus 1, that's equal to minus 1 by 20, and we have verified Green's theorem. LHS equal to RHS, and we have verified Green's theorem.